Let's start with the big question. How does AI actually create a detailed image from a simple text prompt? The secret ingredient is something you'd never expect, pure random noise. Think of old TV static. Every major image generation model today starts with this static and step-by-step refines it into a clear picture. But why start with noise? It comes down to three simple reasons. First, it's incredibly easy for computers to generate. Second, it introduces randomness. If you ask the AI for a picture of a teddy bear reading a book 100 times, starting with different random noise ensures you get 100 uniquely different images instead of the exact same bear every single time. And third, the math behind it just works perfectly. Think of it like a sculptor. A sculptor doesn't start with a finished statue, they start with a rough, unshaped block of stone. The AI acts just like Michelangelo, chipping away the meaningless noise to reveal the masterpiece hiding underneath. To train the AI to be this master sculptor, researchers use a clever two-part strategy. First is the forward process. Imagine taking a crystal clear photo from your camera roll and slowly adding a little bit of static to it, step by step until it is completely unrecognizable. It's basically ruining the image on purpose. But here's where the magic happens, the reverse process. The AI studies exactly how that noise was added, and it learns how to undo it. It looks at a completely noisy image and asks, what static do I need to subtract to get slightly closer to the original photo? It does this over and over, training itself until it can take a screen of pure static and magically carve out a perfect picture. The crazy part? The insanely complex math behind this training boils down to a surprisingly simple goal, just guessing the exact noise that was added and correcting it. There was just one massive problem with this early on. This step-by-step cleanup process required 1,000 tiny steps. If you wanted to generate just one image, you had to wait way too long. To fix this, researchers came up with a brilliant shortcut. Instead of taking 1,000 random tiny steps, they figured out a way to skip steps and make the cleanup path predictable. By removing the randomness during the generation phase, they could speed up the process by up to 50 times, without ruining the image quality. That is exactly how tools today can spit out gorgeous art in seconds instead of minutes. Starting with the broadest possible question, how do we get AI to generate a brand new image out of thin air? Imagine you have a massive collection of data, like pictures of teddy bears. Our goal is to start with something easy to create, like pure random noise, and somehow mold it into a real, high-quality image. To get from pure noise to a real image, you need a sense of direction. Enter the score. Think of the score as a compass in a dark forest. Mathematically, it is the gradient of the log of the probability distribution, but practically it simply points you in the direction where real data is more likely to exist. By following this compass, a technique called Langevin sampling allows the AI to take steps toward the actual images. But there is a huge catch. We don't actually know the true distribution of all real images. So our compass is basically broken from the start. The brilliant workaround for this is called denoising score matching. Instead of trying to map the unknown, we take our real images and intentionally add Gaussian noise to them. Why? Because the math for a Gaussian distribution is incredibly easy to compute. By optimizing our model to match the score of this intentionally noisy data, it acts as a perfect proxy for learning the true data distribution. This introduces a classic trade-off. If we add only a little bit of noise, our target remains accurate, but our compass won't work in areas of pure noise. If we add a lot of noise, our compass works everywhere, but the final target becomes distorted. The elegant solution is to use multiple levels of noise. You start generating your image using a massive amount of noise to point you roughly in the right direction. Like driving from Stanford to New York, then, as you get closer to the real image, you gradually reduce the noise level to refine the precise details. Going down another level, instead of using arbitrary discrete steps for this noise, researchers realized they could map this entire process using continuous time through stochastic differential equations. By treating the forward noising process as a continuous flowing mathematical equation, we can mathematically run it in reverse to generate clean images.
Think of it this way. Imagine you have a fleet of self-driving cars scattered randomly in the desert. This is your initial distribution, basically pure noise. Your goal is to move every single one of those cars until they form a specific pattern, like a giant logo. This is your target distribution. In diffusion, we used a compass to find the way. In flow matching, we provide a vector field, A vector field is like a set of GPS instructions for every point in space and time. It tells each particle exactly which direction to move and how fast to go. If these instructions are smooth and consistent, what mathematicians call Lipschitz continuous, then every particle follows a unique, predictable path. The secret sauce that makes this work is the continuity equation. It's a principle borrowed from physics that ensures conservation of mass. It basically says that as we move our distribution from noise to clean data, we aren't losing or creating any probability out of thin air. We are simply transporting it. But here's the problem. Training these models used to be incredibly slow. You had to solve complex integrals just to learn a single step. The breakthrough in flow matching is a technique called conditional flow matching. Instead of trying to learn how to move the entire desert at once, we simplify the problem. We pick one starting point of noise and one target point from our training data. We draw a straight line between them. This creates a probability path that is incredibly easy to calculate. By aggregating all these simple straight line paths, we create a marginal vector field. It turns out that training a model to match these simple straight lines is mathematically equivalent to the complex version, but it's much faster and more stable. At inference time, when the AI is actually creating an image, it starts with a sample of noise and follows this learned vector field step by step until a clean image emerges. While these paths can sometimes get curved or tangled during training, researchers use a process called reflow. By iteratively straightening these paths, we can eventually generate high-quality images in just a few steps, making AI faster and more efficient than ever before. This story begins with a problem. How do machines represent the world? As humans, we see pixels, millions of tiny dots of red, green, and blue. But for a computer, treating an image as a million individual dots is overwhelming. It's too high-dimensional, full of redundant information, and mathematically spiky. If you change just one pixel, the computer gets lost. To solve this, researchers created a bottleneck. Think of it like a translator. We take a massive image and feed it into an encoder. Its job is to compress that image into a tiny, meaningful space called a latent space. To make sure we didn't lose the soul of the image, we use a decoder to blow that tiny representation back up into a full picture. If the output looks like the input, we know our compressed version was perfect. This is the autoencoder. But there was a catch. Standard autoencoders produced spiky spaces, where a small step in any direction led to digital static. So, we moved to variational autoencoders, or VAEs. Instead of mapping an image to a single point, we map it to a neighborhood or a distribution. This forces the latent space to be smooth and structured, which is essential for models like Stable Diffusion to work. However, these early models had a blurriness problem. Because they were penalized for every pixel they got wrong, they played it safe by averaging colors, resulting in hazy images. To fight this, we introduced two judges. First, a perceptual loss judge that doesn't care about individual pixels, but looks at high-level features like textures and shapes. Second, an adversarial judge, a second AI called a discriminator, whose only job is to spot fakes. This competition forces the generator to create crisp, realistic details. Now that we have a perfect, smooth, latent playground, how do we tell the AI what to draw? This is where conditioning comes in. We take your text prompt, like a teddy bear reading a book, and turn it into math using a transformer. This model uses attention to understand that the word reading refers to the teddy bear. Finally, we guide the creation process. Using classifier-free guidance, the AI actually imagines two versions of the image at once, one based on your prompt and one that's completely random. By looking at the difference between the two, it pushes the final image to follow your instructions more strictly, resulting in the high-quality AI art we see today. This entire architecture, from compressing pixels to guiding the noise with text, is what allows a machine to dream up anything you can imagine.